Good evening and welcome to the final Carl Cymru session. This evening's session will be run by Ms Stevens from e-sgol Peda. She'll be looking at Unit 2, Thermochemistry. Put a link into the Q&A section for you, and we appreciate your feedback on the session. And I'll pass you over to Mrs Stevens.
Good evening to you all. Now, if you have been tuning into these sessions, then you already know that both myself and Mr. Black have been tailoring our sessions this time more to the advanced information we've been supplied with and focusing primarily on kind of exam technique and tackling particular exam questions. Okay, so as you can see there, you can see that the thermochemistry is quite a high ranking proportion of your paper this summer. So as a consequence, that's what I'll be focusing on this evening because Mr. Black did his alcohols last week. Okay, so to do with the specifications, I'm sure you're well familiar with this now because most teachers do start on the beginning of Unit 2, so 2.1. But let's also remind you, take this opportunity to tell you the calculations that were primarily Unit 1, that those calculations are expected as part of the entirety of Year 12, so please do not lose focus on them. You have to know that content for Unit 2 as you will in Unit 3 and 4 of next year as well. So don't lose focus of that. It is also worth mentioning that there was an earlier session that covered the content of enthalpy. Back, I think it was in spring 2021, so one of the very earliest first sessions we did. If you want to know more about the in-depth content of itself, then I would suggest you go back, because what I'll be doing, I will be going through the content, but maybe at a quite hefty pace. So if you need a bit more in-depth, please go back to the 2021 spring session that was primarily on just the enthalpy as opposed to the exam technique. Okay. It is also worth mentioning, okay, you've got the chemistry experiments on film, and I think that is a absolutely crucial resource that you should be accessing on a regular basis. So it's available for physics, chem and maths, as you can see there. But it is such a valuable resource, and I hope that you are all using this to the best of your ability. The link I put up there for you, but I'm sure that your teachers themselves are also showing you these. So they've been written primarily to assist you in preparing for carrying out the experiments in the lab books. So for the thermochemistry section, there are two specified ones, which is the indirect determination of enthalpy change and also the one by combustion. So it's well worth going onto this website and taking yourself through the films if you haven't already done so. The one I've got here, I couldn't get the one for Chemistry for You to play because it's actually an internal website that plays it, but it just takes you through.
Ms Stevens, I'm not sure we can hear you at the moment.
At all, or?
Can hear you now.
Okay. Right, so I'll just go back to that slide. Okay, so what I was showing there, apologies if you couldn't hear the volume or myself, it was just taking you through the experiments on film that is really worthwhile. If you haven't already done so, please start using and looking at that website, okay? Right, so going into the content today, enthalpy changes, there are quite a few things that you obviously need to be familiar with for this unit. So what is meant by enthalpy changes? What is meant by standard, and that is something that kind of sneaks under the radar with some pupils, and how to go about tackling different elements of it. So I'll run through the entirety of that before I tackle the first exam paper. So thermodynamics, way back in probably end of Key Stage 3 into Key Stage 4, you learnt this fundamental law, which is that energy can't be created nor destroyed. Okay, but it certainly can be converted from one form into another, and that is exactly what thermochemistry, this section of the course, is all about, really. Okay, and then building upon that, in the fourth unit of Year 11, you came across this unit, of course, which was the exo-endo unit. So you're familiar with the fact that exothermic reactions give out energy and endothermic ones, energy is hence absorbed. Okay, so that's nothing new to you, I hope. Okay, and then when you are asked to define things, that again tends to throw a few people because it does say no formal definition is needed. Please don't let that fool you. You do need to know what is meant by it. So I suggest you have a familiar definition of enthalpy that just sits right with you, that you will be able to kind of reproduce and exam stress conditions and know that you are confidently ticking all that boxes. Okay, so enthalpy, it's only my own one, but it's a measure of the heat content of any substance at a constant pressure. Now, you can't measure the actual enthalpy of substance, but you can very much measure the enthalpy change, okay? And as I'm hoping you are now familiar with, you represent it with that delta H symbol, okay? Now, recognizing these energy diagrams is also another skill I really encourage you to get under your belt, okay? So recognizing an endothermic and an exothermic energy path or a reaction pathway is crucial, and I will be very clear that you need to know and be confident in being able to label those two things out, which is the activation energy EA as well as the enthalpy change itself, delta H. So with a kind of exothermic reaction, it's often, they're not going to ask particulars for you, okay? I can't remember them asking you to specifically label a delta H or a delta E with respect to a value, but they do expect you to show it and what it represents. So as a sketch wise, it would literally be a case of you start high, there is always a hill to climb because every reaction has an activation energy. So you go over the hill and you end up at a lower, and that's just a simplistic representation of an exothermic reaction. So flip that on its head to an endothermic sense. You start off low in this sense, there is a massive hill to climb and you don't get full payback and you end up higher than where you began. So again, you need to be confident in being able to label and identify where the activation energy is in that diagram and where the enthalpy change is in that diagram. Okay, so sketch is exactly what it says. It's a sketch. So quickly just sketch it as I do again, just start low, go over the hill, start to end higher than you began. Okay. So sketching, quick, 1 marker, 2 marker maximum if you are also asked to match it with the EA and the delta H diagram labeling. Okay, so let's just take just a few seconds just to be clear that you understand what is meant by standard. Now, standard also has this crucial symbol that you are hopefully also familiar with already, which is it is then assumed that that reaction that you are describing has taken place under these standard conditions of 100 kilopascals, 1 atmosphere, more specifically for most of you, unless you are also studying side by side with chemistry, physics, because they will go in pascals in physics more commonly than atmospheres, and a temperature of 298 Kelvin. 298 Kelvin is indeed 25 degrees C, but please, for the sake of not complicating things like the gas law equations that you might also need to be using, get into the habit maybe of using a Kelvin as a measure of your temperature, so 298, okay? Standard enthalpy of formation. Now, to do with formation, it is important, okay, that you understand that there are certain conditions for formation, okay? So highlighting certain things, let's be clear, it is for the creation of 1 mole, and we'll come to the relevance of that in a minute, okay? It has to be under standard conditions, as you see there, and it's for their elements, but those elements also need to be in what is called their standard state. So it's often a kind of wasted mark, I suppose. Then you might have an equation for creation or formation of carbon dioxide from carbon and oxygen. Now, carbon being a solid, whilst carbon dioxide is a gas, without these state symbols, you would not get credits. Okay, so they'd expect you to have state symbols when you're representing enthalpies of formation. So that is an easily lost mark and quite a commonly lost mark. Do not forget it. It is very important. Okay, it is only 1 mole. So again, when you're writing a balanced equation during an enthalpy of formation, it's a bit contradictory, I suppose, because very often what you're encouraged to do is double up things if it means that you have or you require 1.5. Like you see here, you require half a mole of oxygen. Well, what most pupils instinctively want to do then is to double things up. So you can often see pupils representing it with maybe a 2 there. That is eliminated and you make 2 waters. Now that is a balanced equation, but it isn't the standard enthalpy information of water because it is dependent on creating only a single mole, so 1 mole. So do not fall into that trap either. Okay. Right, combustion. All these are very, very similar, so I'm going to skim through the next few. Okay, so the enthalpy change when 1 mole, again, 1 mole of a substance undergoes complete combustion. So with complete combustion, they're assuming that there is sufficient oxygen there that it creates the expected oxide. So when you combustion of carbon, you'd get carbon dioxide, not the byproducts of carbon monoxide that is only created when you've got insufficient oxygen. Okay, so enthalpy of neutralization doesn't really creep up very much anymore, but it is the enthalpy change when 1 mole of water is created from its constituent ions in solution. Okay, and not that you expected to memorize it, but usually if you've got a strong acid and a strong base or a strong alkali, then it tends to give a value in the region of -57 kilojoules per mole. Right, so bond dissociation enthalpy. Now this you have to be familiar with, but it's just building upon what you did in Unit 4 of Year 11 again, really, which is that you understand that in order to break apart a bond, okay, you need to input energy and that requires energy. So that's an endothermic process. Whereas when you create new bonds, when you make new ones, create a product, then that liberates or gives out heat. Okay, so it's the same energy of a bond, whether you're breaking it or whether you're creating it. So be clear in that it's not some weird trick that they're trying to catch you out on. If they give you a table of bond enthalpies or bond dissociation energies, it's the same whether you're breaking it or making it, which you'll see me use very soon. Okay, not expected to memorize them. So what you're expected to do is be able to use them. So if you've got methane, for example, okay, if you're asked to work out the enthalpy of breaking that, then obviously you'd have to identify the CH bond. So there it is there in the table. And then you'd have to go 4 times 4 and 3. Okay, so it's a case of just confidently and calmly looking at what bonds are being made and what bonds are being created and broken in any constituent part of that reaction. Okay. To be clear, just because it tends to be something that leads to some errors, I get rid of that so I'm not hiding too much from you. Okay, units. This is often either left out or given incorrectly. Okay, so units is usually specified as kilojoules per mole. Otherwise, the numbers you are handling are extremely large. And as a consequence, it usually is converted from a joules into a kilojoules, but you'll see me doing that in an exam question very soon. So Hess's law. Now, again, you have to have a definition under your belt, I would say, to be able to confidently define it, even though there's no formal definition. So the enthalpy change is independent of the path taken. It's a very simplistic one, but it ticks all the boxes. So if you don't have one that you're confident yourself, I'd say happily steal mine there. Okay, so the enthalpy change is independent of whatever route is taken. So I put it into context to you. I've mentioned there the carbon dioxide earlier. So if you burn or combust carbon, its natural product will be carbon dioxide. But the energy to convert carbon to carbon dioxide would be the same as, so if I start with carbon and I end up with being carbon dioxide, it'd be the same as if I initially converted into carbon monoxide and then further oxidized or combusted that to create the carbon dioxide. So this route here, okay, which is the, if you can see there, the clockwise direction, would it be exactly the same as if you did the initial combustion to carbon monoxide and then combusted it further to carbon dioxide. So clockwise is equal to anti-clockwise. That is another thing I would keep in mind. Okay, right. So the enthalpy change going from A to B, you can see there, it's exactly the same as if you did it in stages. Now it tends to be a Hess's law cycle, tends to be triangular, so it tends to be three-sided, but it can be multiple sides. And when you get into year 13, they get to become even more complex into what is called Born-Haber cycles at that point. But they tend to be quite good to you in year 12 and keep it quite simplistic. So it tends to form a triangular shape when you're dealing with them. Okay, so why use Hess's law? Why is it useful? Well, you apply Hess's law and use it for a variety of reasons, really, but it would be in situations where you can't directly measure an enthalpy. So things like lattice enthalpy, you can't directly measure that, or if you have got a reference to the bond enthalpies, then you'd have it. You can use Hess's law to work out something that you don't know. Enthalpy change a reaction from enthalpies of combustion. You can work out how much is needed to create a compound if you know how much it takes to combust that as well as elemental form. Okay, so it's a really useful skill that requires you to do less or more simple chemistry sometimes. So if direct reaction is too complicated or dangerous in some situations, you would do it inadvertently using Hess's law. Okay. So this is not really a big step up from GCSE. So you can apply enthalpy of reaction from bond enthalpies. So you can see there, if I've got let's get my head together there, exothermic, yes, an exothermic reaction. Okay, then you'd work out the bond enthalpies of reactants, which would require you to break the bonds, and you would subtract from that, so minus the bond enthalpies of the products. So in GCSEs and all the way through to the end of 13, my pupils are quite familiar with me chanting, it's break, take away, make, break, take away, make. So you break all the bonds in the reactants and you subtract from it the energy needed to make the new kind of product bonds. Okay, so it's break, take away, make. That's the chant that my pupils are very familiar with hearing. So in this type of example, you've got ethene there. So you've got hydrogenation of ethene, turning it from ethene to ethane. Well, that's all you need to do is work out how much energy is needed to break apart all the bonds in that ethene and hydrogen molecule. So you've got, clearly see there, you've got one or a singular CC bond. It's got a value of 611. You would not need to know these. These would have to be provided to you. Okay. Or inadvertently, you could be able to work it out if you've got all the information, but not expected to memorize them. Okay, you can see that diagram. You've got a 4 CH bonds is you've got a single HH bond, and that equates to, therefore, adding them all up to 2,699. If you then remake the new bonds in the products, okay, the only difference ultimately is that you are multiplying by a bigger number. So you've now got 6 CH bonds. You've got a singular CC bond now as opposed to an unsaturated C double bond C. Okay. And that equates then to 2,824. So that is the breaking, that is the making. Okay, so as I said, the delta H is break, take away, make. Okay, so in this sense, what you'd be expected to do is subtract 2,824 from 2,699, and it equates to having minus 125. That minus tells you that it is an exothermic reaction. That's the other thing you should have carried through your knowledge. Negative enthalpy changes are indicative of an exothermic, whilst a positive enthalpy is indicative of an endothermic process. Okay, right. So enthalpy of reaction from enthalpies of formation. This is invaluable recall, I would say. So if you're using enthalpies of formation, the immediate and straightforward equation you need to apply is that you have the enthalpies of formation of the products, take away the enthalpy of formation of the reactants. Okay, so do not get it confused, because in this sense, it was in a way reactants take away products when using bond enthalpies. But when you are handling enthalpies of formation, it's directly this equation, which is the formation of the products, take away the formation of the reactants or reagents. Okay, so you can see there that calculate the standard enthalpy of the following reaction, given that the standard enthalpies of formation of water, nitrogen dioxide, and nitric acid are 286. Just a quick example there that basically emphasizes the fact that you've got 2, 4, 4. Okay, you need to be multiplying these enthalpies of formation, which is why it is 4 times the delta formation of nitric acid, 2 times the formation of water, 4 times nitrogen dioxide, and a singular oxygen. But it is worth noting that the value for oxygen is in fact 0 because it's standardly or in standard form in its elemental form already. Okay. So that equates then to having an answer of minus 252. Again, it is negative, signifying a exothermic reaction. Okay. So you can do lots of manipulation, and I'm not going to dwell, I did say from the beginning I wasn't going to dwell too much on them. I want to get on to the questions themselves, but you can do the same type of approach with enthalpies of combustion as well. Okay. But be crucial difference here. It is now the combustion of the reactants take away the combustion enthalpies of products. So evil as it is, they're very similar, as I said. Okay, but you notice this one for formation is products take away reactants. For combustion, it is reactants take away products. Do not mess them up. Okay. Right, so measuring enthalpy changes. You are not supplied with this equation. You're expected, as is cruel in chemistry, to recall most of the equations. You're given values to use within equations, a formula, but you're very rarely supplied with the formulas themselves. Should you be expected to recall that equation there? Okay. So it says here on complete combustion of 0.18 grams of hexane, there was a rise in temperature of 100 grams of water from 22 to 47 degrees. What is the enthalpy of combustion? Well, using all the numbers, first thing to note here is that you have to be careful with using the right numbers in the right place. Sometimes you end up with 2 masses, or you think you've ended up with 2 masses, and you haven't. Okay, so for example, this M is not the mass of the hexane, so we're not using that. It's not that yet. Okay, that mass is the mass of the solvent in this case, which is the 100 grams of water. Okay, C is the heat capacity. You'd have to be provided with that value. Okay, and the delta T, they sometimes give to you. Sometimes they give you the initial temperature and they give you the end temperature, and you have to just do a little bit of a quick subtraction to get the delta T. Okay, in this case, what we have is a calculation that gives you a value of 500 kilojoules per mole. Okay, now I said there kilojoules. Okay, be careful because the value of your units should be led by the unit of your C, your heat capacity number. Okay, so sometimes it's supplied as a kilojoules per kilogram, and sometimes it is provided as a gram or joule per gram. Okay, now if I go back, apologies, it's a bit pale, but you can see that the specific heat capacity I've used in this case was kilojoules per Kelvin minus 1 kilograms, which is why I used or inputted 0.1. So I converted the 100 grams there into 0.1. And the temperature change was 25, which is the difference between 22 and 47. And it gave you an answer, therefore, in kilojoules, not joules. Okay, so take care and take guidance from the unit specified for C. Okay. Now, I'm hoping that you've all had hands-on of carrying out enthalpy changes. Polystyrene cup is the simplistic approach that most schools take with lids on, etc. But I'm hoping that you've had an opportunity to collect information and data yourself and then learn the skill of extrapolation. So this is what this skill here is that you have certain plots being taken. So usually take a recording every 20 to 30 seconds. But there's obviously a time delay between the addition and the peak of the max temperature, in which case you need to then extrapolate back on your graph. That is skill, again, I'm hoping you've got under your belt. The experiments on film is particularly good at giving you hints about how to do that. And then the other clip at the beginning of this PowerPoint I took from YouTube, that takes you through in even more detail the approach of plotting graphs and then extrapolation back from that data. Right, so There are lots of different questions that have come up in the past on thermochemistry, so I'm going to hopefully go through a few of these. There are lots of examples. When you have time, hopefully, when you're getting nearer the exam and you're going through a bit more in-depth revision, get this PowerPoint, which will be available on the Carlam Cymru website, and just stop it and go through it at your pace. So there's another example there for you. I'm not going to dwell too long on. So this is the crux of what I wanted to make sure you are building your confidence in, which is actually tackling past paper questions from the WJC, and what little nuggets of information I encourage my pupils to extract at what point. Okay, so this is a question. Now, you're allowed highlighters. I'm not sure how many of you use them in an exam, okay? But I always encourage my pupils to kind of highlight or take extracts of information from the beginning. So if you read this question, there are key things that are important. So it tells you you've got 50 centimeter cubed of water, or of the acid in this case, 1.4 molar. That is going to come in useful at some point. And then later on, they told you that we had calcium oxide of 1.9 gram, and there was a temperature rise of 20.5. So this time they didn't give you a before and after temperature. They went straight ahead and told you the delta T that you will need to be applying into that equation. Okay. It then went on to ask you to use the equation to show that the hydrochloric acid initially was in excess for the reaction with calcium oxide. So how do you decide whether it's excess or not in excess? Well, it's a slightly problematic in the fact that you've got one that is clearly an acid in solution, so you've got concentrations to be handling, and then on the other side you've got a mass of calcium oxide to be handling. So if you look at this, from GCSE in a sense, the equation they need you to apply is N is equal to M divided by MR. Okay, so it told you that you had 1.9 grams. The MR of calcium oxide is 56. And that equates, therefore, to having 0.0339 moles. Okay. On this side, the equation that you need to manipulate and rearrange is concentration is the number of moles divided by the volume in decimeters. Okay. So rearrange that to get N. N is equal to C times V. It told you that the concentration was 1.4, and it told you that you had 50 centimeters cubed of it. Do not forget, it is in decimeters. So it's 1.4 multiplied by 0.05. That is the conversion of centimeters cubed into decimeters by division by 1,000. So divide by 1,000. And that gives you then an answer of 0.07. Okay. Now then, if I go back to the equation, what happens is that you got a ratio of 1 to 2. So if you have 0.07 moles of the acid, in theory, that should be able to neutralize 0.035 moles of the calcium oxide. Well, we don't have that many, okay? Because if you look at it, what we have is 0.0339, which means that this side must be the one in excess. And that's how you tackle this type of question, okay? So calmly work out, there were 3 marks, okay? So there's plenty of time. Do not rush these types of question. You've got one side which requires you to apply one formula, so N is equal to M divided by MR. The other one still needs to work out the number of moles, but rearranging C is equal to N divided by V. The classic mistake here, I would imagine, is that people would forget possibly that there is a stoichiometric ratio to consider up here. If even, as it happens to be, if you hadn't done it in this case, then it still would have been blatantly clear that it was excess, because you'd been handling 0.07 versus 0.0339. So even without the remembering of the stoichiometric ratio, you would have got away with it in this case. It's not always the case though. So be careful to look back at the equation in question. Okay, so you can see there, exactly the same numbers as I extracted there. You've got 0.07 that would potentially neutralize 0.035. It doesn't have that much to neutralize, so it tells you that the acid is in excess. The follow-up question was then, calculate the energy released in the reaction between that calcium oxide and the hydrochloric acid. So then what we have to do, okay, is recall and use that following equation there. So Q is equal to M times C times delta T. So extraction of the information. We know we've got 50 centimeters cubed. That was in the question that highlighted that bit earlier. We know that they have to provide you with a specific heat capacity of water. It's usually in the data sheet and the front of that. So it's specified in the WJC one as 4.18. It told you the temperature rise, the delta T was 20.5. Putting all that together, apologies, if I put all the numbers of those together, that means that I need to go Q is equal to 50, which is the mass of the water. And I'm using 50, I'm not converting it to kilograms, because if you look at my value for C, it's joules per gram that they've given you. So I'm going to keep it as grams. So I've got 50. I've got the heat capacity, which is 4.18. I have got the delta T as being 20.5. Calmly insert that into a calculator and it gives you out the value 4,284.5 joules. Okay. So it then asks you to calculate the molar enthalpy. So that's all that requires then is this equation. So you are taking your previously calculated value for Q and you are dividing it by the number of moles. Okay. As it happens in this question, because of the way they'd scaffolded it, we've already worked out the number of moles in the previous slide, if you remember correctly. Okay. So remember, I've already worked this out. So some of the work's already been done. Okay. So in this sense, that's all I need to do is take the number of moles that I'd calculated, which is 0.0339. Okay, and divided the previously calculated 4,284.5 by it, giving me an answer of minus 126. Now, where did that minus spring from? Well, okay, it told you that there was a temperature rise. That tells you you must have the kind of common sense, I suppose, but it's dangerous to say that sometimes, but you have to be aware, therefore, that your enthalpy answer will in fact come out to be negative, because that's what is indicative by an exothermic reaction where a temperature goes up, is that the enthalpies are negative. So even though it wasn't part of my equation, it was very much, and this is why, if you notice, they'd asked then for the sign. It was an additional element of the question that they were checking whether you had that little bit of common sense and you had to remember to put in as a minus. Okay, so do not forget little minor details like that. They are important. Right, the value of molar enthalpy change of reaction for the reaction between calcium hydroxide and hydrochloric acid is minus 196. So so using Hess's law and your answer to the previous question, calculate the enthalpy change of reaction for the decomposition reaction as follows. It did give you a little bit of a safety net here, which said that if you failed to attempt or had a reasonable answer to part one, they gave you a dummy value to use. Okay, so here, you need to construct a triangle, you need to construct a cycle. So if you look at it, what we've got here, you've got calcium hydroxide, okay, and it's asking you the enthalpy of making, as a product, calcium oxide and water, okay? Well, what we'd previously worked out, okay, was the reaction of, if you react it with HCl, okay, you will get, there is an alkali, and an alkali and an acid would give you the same products. So in this case, it would make the salt calcium chloride, okay? It also makes water. In the same sense, you've got a base here, again, would react with HCl to make exactly the same products, okay? So you would get the same product. So what you're looking for here is the knowledge and application of the values you've got. So it told you that it was minus 196 for that. That is given for you. And this is the one we'd calculated, which is minus 126.4. Okay. So putting all those numbers up, don't forget it is clockwise is equal to anti-clockwise. So in this sense, what we'd have is the unknown, or the one that they've asked us to calculate, is a clockwise arrow, but as is this is also clockwise. So x plus minus 120. Oh, for some reason it's gone funny on me. Minus 126. Oh, see, this pen was behaving until that minute. Let's go back. Right. So x plus the other one we know, which is minus 126.4, is equal to the other arrow, which is minus 196. If you rearrange that to get x on its own, you will in fact come out with a value of minus 69.6. Okay. And that is simply by rearrangement of this entire calculation, which is clockwise arrows is equal to anti-clockwise. Keep that in your head. Make it into a little chant if need be. Okay. Right. So just a quick check of time. Got a few, yeah, good significant number of minutes left, so that's okay. Right. So that is exactly as it says. So they give you credit there for construction of the Hess's law or Hess's cycle correctly in the correct direction, and then the calculation being accurately worked out to give, as I said, the value minus 69.6. Right, suggest two changes to the apparatus. Now, again, they tie in with your practical skills here. It's assumed that you are carrying out those specified practicals from your lab book, and the two ones that are specified, if you've had hands-on with, which I hope you all have, would have then opened up this type of thinking outside the box question, which is, all right, this is the experiment I carried out. How can I make it better? Okay. So if I think about the apparatus I had, that was the apparatus in the picture from the question itself. So I've got a beaker there with a 1 centimetre division thermometer. It told you that you are adding 50 centimetres cubed of acid. Right, what's the relevance of that? Well, first off, let's focus on this then. 1 centimetre division thermometer. We know that there are thermometers out there that are more accurate than that. So one clear improvement would be to use a thermometer with smaller divisions. That would supply you with greater accuracy. The other thing is I've got a big beaker here. It's not insulated, so you could suggest that you insulate it, wrap it in a bit of cotton wool whilst you're carrying it out, or I don't know, stick on a lid there maybe, and you have the thermometer going through a hole. If you've had hands-on of using this, as I said earlier, this classic polystyrene cup type of question, then all of these things will come to the forefront of your mind, and you know, well, I used a lid. There must be a reason I'm using a lid to contain all that energy to limit the heat loss to the environment. So using a lid, using insulation around that beaker, using a better thermometer with smaller divisions. And here is a bit of a sneaky one, and I'll be honest, I wouldn't immediately think of it, but the fact that they'd given you a measurement of the acid as 50.0 suggests that you've either used a measuring cylinder or a pipette. Now, you do have availabilities of burettes, which have a much more small division. So you could use a burette and you could therefore measure to 2 decimal places as opposed to 1. So that, I'll be honest with you, often I think would have sneaked under my own radar, never mind my pupils one. But I'm hoping all of you would be confident in saying things like minimize the heat losses by using a polystyrene cup, or wrap it in cotton wool, or have a lid, okay, have a thermometer that reads to a greater accuracy or precision, and then use a burette was also a valid marking point when this exam paper came out. Okay, right. Method odds, a liquid at room temperature and its molar enthalpy of combustion can be found directly. Now, write the equation corresponding to the standard enthalpy of combustion of methanol. It's a very easy question, okay? However, it requires you to remember what I hopefully emphasized to you clearly earlier, which is it has to be for the creation of 1 mole, Okay, so I've got methanol, which is CH3OH. It's going to make the 2 expected combustion products of carbon dioxide, one of them, because there's only 1 carbon in methanol, and it's going to make 2 water molecules. Now, if you then, before you start calculating your oxygen, come back to it, look how many oxygens I need. So I need 2 oxygens in the carbon dioxide here. I need 2 oxygens in the water, that's 4. But don't lose sight of the fact that there is already 1 there. So classic mistake would have been to put in 2 moles of or molecules of oxygen. It's not, because 1 oxygen is already in that methanol. So I in fact only need 1.5 molecules of oxygen. It's only requiring the formation of 1 or combustion of 1 mole. Okay, so do not get sidetracked by that. The other question, if I go back to it quickly, looking at this one, it asks you to draw and label a suitable apparatus that you can do for the combustion experiment. This is where, as I said already, it is invaluable that you are being let loose on these practicals in the lab yourself. If your teacher, to demonstrate anything else, is reluctant, then please encourage your teachers to let you loose on these, even if it means you go in on a lunchtime or whatever. Ask your teacher, I would like to practice these experiments in my lab book, please, because they are invaluable for getting you to put this type of question into context. So this was just a case of recalling this sort of apparatus, okay? And this sort of apparatus is what you yourself would have used. So it's having the spirit burner filled with the methanol at the bottom, is having the, hopefully, the common sense to know that that spirit burner needs to be relatively close. So look, there's very little gap there between the spirit burner and the calorimeter, you'd call it. It's ultimately a container that contains the water. I would say you need it to be often copper based. That's what our calorimeters in the school are, but you can even use a plain straightforward glass beaker. So you have the calorimeter very close to the spirit burner. You have a thermometer to measure the temperature rise as it's happening. And that's it. That's the only apparatus you need. Okay. But the equation of the combustion of ethane is shown below. Use this and the value for this for the average bond enthalpies in the table to calculate the average bond enthalpy of the CH. Now this, I think, will be the last question I go through with you. And that's because it was a bit of a sneaky one in the sense that they didn't give you all the values. They gave you the answer, which was the enthalpy in whole, and asked you to work backwards from that. So if I look at what I've made there, okay, what you can ultimately see in ethene is that I've clearly got a C double bond C. I've clearly got 4 times CH, and I've got 3 times O double bond O. Now numerically, that works out to be 614 using the bond enthalpies they'd given me. I don't know what that is, so let's just label it 4x. It's an unknown value. And then that equates to being 4 times 495. Okay, that means I have got a total of 2,099 plus 4x, because I don't know what the x is yet. On this side then, what we have is 4 C double bond O's. And I have got also 4 OH bonds. Okay, numerically, they'd given us those bond enthalpies, so that works out to be 4 times 799. And then the OH bond was specified as 465, so it's 4 times 465. I've got all the enthalpies and bond energies I need then, so that equates to being 5,056. Okay. We knew from the question specified that the delta H, if I go back to the question, was specified as being minus 1,387. So let's use that. That means it's break, take away, make. So break, take away, make. So that equates to being 2,099 plus 4x. Take away the value we worked out there, which is 5,056, is equal to minus 1,387. If you rearrange all of that to get 4x on its own, okay, 4x then works out to be, mathematically, 1,570. So x is therefore going to be 1570 divided by 4, giving you a value of 392.5. So there's a bit of a, I don't know, odd angle to take on this type of question, but I liked it. I'll be honest with you. It required you to be really sound in your knowledge of what you were doing, but a quicker way of asking it. So I quite like this one. Okay. So as it says there, it works out to be 392.5. They would have accepted quite happily 393 because unless you specify it in your question, the DEMJC have got in very small print in some part of the spec that mathematical answers can be given to 3 significant figures, and that is acceptable. Okay. Right, now there are lots of other past papers in this PowerPoint. It was never the intention to finish it, but if I encourage you to then work your way through the next few past paper questions as part of your revision, I'm hoping you'll find it really useful. Okay. I'd also like to just quickly draw your attention to the last few slides before I end for this whole season. In fact, isn't it? Because this is the last session this year. Is kind of resources that I've told my pupils to use, which is these things, which are the knowledge organisers prepared by the DEMJC. So that's the one for the thermochemistry. And also just to give you quick encouragement, as I did my last session, try varying your revision as much as you can. Make it as kind of interesting and purposeful as you can. Chemistry is a hard topic. So try jazzing it up if you can by using a variety. So my pupils, I encourage to use things like Quizlet. It just gives you a variety of things. So it can be as simple as matching games. It can be flashcards. So that's what this is, one of the flashcards. What is an enthalpy change? The answer comes up when you click it and it gives you the answer. These are the matching games that they had. So you'd match the right statement to the right thing. So it's just a case, it's interactive. You have it on your screen and you just kind of move them around. It just makes revision a bit more interesting, but still surprisingly educational. So hopefully you found that useful. And I encourage you to start revising as soon as you can, but take enough time to have downtime as well. So hopefully we'll see you in the next set of revision sessions when you all return to your A2 studies, I hope. And until that point, good luck into the summer.